Hi, everybody. Just checking my mic here. Sorry, I had an issue with my headset just now that I was diagnosing, but it seems like everything is okay. Welcome back to Chem 140. We are going to be continuing with our discussion of ionic compounds today, probably finishing that up. We might move on to covalent compounds, if we have time. Administrivia stuff to be aware of. Lab worksheet number 3 is due this week. It's due on Thursday. Lab worksheet number 2 should have been returned to you. You can get that on Canvas by checking the assignments page and clicking on lab number 2. You can download the file that you uploaded. I have graded it and written all over it, put editing remarks, and painted it yellow, basically. All right. If you have any questions about your assignments, always send me an email. Take a picture of anything you're asking me about so I can see it. I have all your files still. I don't delete anything for at least a year. That's just school policy. Hang on to everything for a while, and then once it hasn't been claimed or asked about, then we can shred it. I believe that this is the slide that we left off on. We were talking about electron transfer and how this actually occurs in elemental matter, such as solid sodium and chlorine gas. And I showed Lonnie from UC Berkeley how he demonstrated the reaction of chlorine gas with sodium metal. Now, in reality, what is going on here is an electron transfer is occurring so that everything ends up with an octet. Sodium has one extra electron here, keeping it from having an octet, which remember 0 and 8 are the octet. Chlorine has an empty space here, and it would do anything to have an electron. Oh, please, sir, give me the electron. So we move the electron over from sodium to chlorine. Now we have the sodium has an octet, chlorine has an octet. As a result of those ions, we have formed opposite charges, which are now attracted to each other. And so that forms the ionic bond. Now, this pattern is going to happen for whatever combination of cation and anion is needed to give everyone an octet. And then the charges will attract to each other to balance out the charges, okay? So we're going to do that in 2 steps. The first step is to make our ions. What ions can form? Those are going to be the ones that satisfy the octet. So we want to first form ions, and they have to have octets. Then once we've done that, you're going to let the ions attract to each other, and those charges will need to neutralize. Whenever we do an ionic bond, we're going to invoke a metal and a non-metal. Can't do 2 non-metals, you can't do 2 metals. We have to have one of each, because one side will be the positive and the other side will be the negative. All right. So let's do some examples here. So let's suppose... In fact, I'm going to go one step earlier. How do we know that we get K plus and S2 minus? So let's go over here. We'll put the problem on here, but we're going to go one step earlier here in our little problem preview here. That's not the paintbrush. There we go. Okay. So how do I know that these are the ions that I am going to form? And the way that we're going to do that is we're going to try and satisfy the octet rule. So here's my potassium. It has 1 valence electron. Why does it have 1 valence electron? You should be able to answer that by now. How many valence electrons does sulfur have? Hopefully you are looking somewhere and writing down 6. Now I have to say, how do I get to an octet? To get to an octet on potassium, remember 0 or 8, I want the shortest way. I'm going to get rid of this one. So I'm going to lose an electron, which means that its charge is now this. How about for sulfur? In order to get to an octet, I have to give it 2 electrons. So it will gain 2 electrons. And so that's how it gets this charge right here. In order to have an octet, you need to have 2 more electrons than what you started with. Now that we've gotten to that part, so now that we know that these are the ions that form, let's talk about how we make the ionic compound. Each potassium is going to have a positive 1 charge as an ion, and each sulfur is going to have a charge of -2. So let's suppose that I put these together and I did this. What would the total charge be? Well, if each potassium is +1, and each sulfur is -2, or sulfide, the overall charge would be that, right? Is this electrically neutral? No, there's an overall negative charge, so I'm going to need more positive charge. So this is not the ionic compound that forms. How do I get the overall charge to be equal to 0? Well, I would need 2 of the positives and 1 of the negatives, right? So in order to make an ionic compound, the total positive charge must equal the total negative charge. Otherwise, when I add the two numbers together, they won't add up to 0, right? And then when I make my formula, I just write what I used. I used 2 potassium ions and a sulfide ion. And so that's how I get the formula of K2S. Now for this first part, I'm going to be just giving you a bunch of ions and say put it together. Then later on, what I'm going to do is I'm going to make you do this whole process. So you're going to have to go from the elements to the ions to the ionic compound. To go from the ions to the ionic compound, you just need to balance the charges. How many positives do you need and how many negatives do you need to get everything to add up to 0? Remember that for the ions, they come in discrete numbers. So if I were to instead do something like, say, this and this, and I were to put these two together, they wouldn't balance out. If I were to put 2 of these together with 2 of these, they still wouldn't balance out. How would this work? Well, we would need to make sure that everything adds up to the same number. So here's 6 plus, and there's 6 minus. So these would work. And I'd get that as my compound. Oftentimes, we're going to just have a simple ratio, but sometimes you end up getting a more complicated ratio, like this 2 to 3. Okay? So when you're making these ionic compounds, keep that in mind. You want to make sure that you balance the charges out. Now, what if I give you a transition metal? The same thing works. You're just going to have bigger charges. In fact, this one I'm giving you here for iron is actually kind of a small number for a charge. 3 is kind of small for transition metals. You can get all the way up to 8. And you'll see that in this class. Oops. Hold on. There we go. All right, same deal as before. I'm going to just write down the ions. How many of each do I need? And really what I do when I'm trying to figure this out is that I will add to whatever side I have less of. So like here, I have less negative, so I need more of that. So I'll do this. That didn't work, so I'll add over here. Oh, that still didn't work, so I'll add over here. There we go. Everything is balanced out. There's my formula. When you are writing an ionic compound, never write the charges in here. Once you've made the formula, all the charges have canceled out, right? So you don't have to write them anymore. Don't put the +3s and the -2s for this compound in the formula. They've already been taken care of. All right. So now I have a bunch of these. There's a second page of these that we're going to come back to in a second here. So on this first page, I have not made the ions for you. So step 1, make ions from the octet rule. And then step 2 is to make the ionic compound. So apply that to each of these 5 pairs of elements. Take KBr, turn K into an ion, turn Br into an ion, make the ionic compound. Do that for all 5 of them. We'll go over the answers together in about 5 minutes or so. See you in a bit. About another minute to finish this up, we'll go over the answer. All right. So, let me clear this real quick. Actually, no. Let's just go to the to this screen. And we'll get rid of this. All right. So these first few are pretty simple because they just work at it. So we got potassium and then we got bromine. Potassium has 1 valence electron and bromine has 7, which I'm just filling in the wrong way, I realize. So first we got to turn this into ions. To get an octet for potassium, I'm going to get rid of its 1 valence electron. That makes it that. And for bromine, I'm going to add a valence electron. That makes it this. Oh, maybe with the R in there too. Yeah, that's important. Now to balance the charges. Does positive 1 and negative 1 balance out? They totally do. So that's going to be the compound that we make. All right, let's do the same thing with the next one. So we got calcium, which has 2 valence electrons, and oxygen, which has 6. Let me make this a little darker here. We're going to apply the same concept. We're going to get rid of 2 electrons to make our calcium have an octet. So that's its charge. I'm going to give 2 electrons to oxygen. So that's its charge. Do they balance out? They totally do. Negative 2 and positive 2 makes that. All right, let's go to the next 2. Actually, I'll just put all 3 of them on the board here. All right, so we got magnesium and chlorine. Magnesium has 2 valence electrons, and chlorine has 7. Let's make some octets. So for magnesium, let's get rid of its 2. And then for chlorine, we're going to give it the 1 that it needs. So there we go. Do these neutralize each other in terms of charge? Well, if I sum their charges together, I'll notice I have too many positive, right? So I need to add more negative. So I'm going to add a second chlorine here. Does that change it so that they are equal? Hey, they're equal now. So now I would write the formula, MgCl2. Oh my goodness, Maya's at my feet meowing. Where is she? Well, she left already. She's sitting behind me looking at me. Let's do sodium and nitrogen. Sodium has just 1. Nitrogen has 5. Let's make octets. We'll get rid of this one for sodium. And then for nitrogen, I got to give it 3. So these charges obviously don't balance out because I have way too much negative. So I need more positives. How many more positives am I going to need? Well, you can probably guess that I got to put 3 of these in here. That's supposed to be a check mark, but... There you go, Na3N. That's the compound that we get there. All right, and then the last one here, we got aluminum and oxygen. Oh, if my pen would stay on the screen here. Aluminum has 3. Oxygen has 6 valence electrons. I'm going to make an octet by crossing these ones out. I'll make an octet over here by adding 2. So aluminum would be +3. Oxygen would be -2. Let's look at the charges. Oh, that's not close. In fact, we're going to have to do this. Oops. There we go. So that makes that 4. That still doesn't work. We'll add another +3. Oh, that still doesn't work. We'll add another -2. Notice that when I'm adding these, I'm only adding the ion in the block of charge that it comes as, right? If aluminum forms a 3+ ion, you have to add them in chunks of +3, right? Because each aluminum ion you add would change the charge by 3. So you can't just add part of an aluminum and get only 1 charge out of it. You have to get all 3. Okay. So be careful when you're doing this. If you're adding more ions, the amount of charge that comes with them is fixed, and that is fixed and determined by the octet rule. Now I have 2 aluminums and 3 oxygens. My formula would be Al2O3. There you go. You're all set. Any questions, let me know in the chat. For the next slide, what I want you to do is I want you to do the same process that we did for step 2 here, making the ionic compound with these transition metals. Oops, there we go. That I have thrown in here, just sort of hodgepodge. So you're going to see that some of these are transition metals and some of these aren't. Tell me the formula of the ionic compound that you make. Now, when you're typing it in the chat, you can't do subscripts. So just type a regular number and I will interpret it correctly. Okay? But type in your formulas when you're ready. We'll go over the answers in just a second. All right, one more minute before we go over the answers. All right, so let's get rid of this real quick. And we'll go over here. I'll just leave all 5 of them on the screen here. That's fine. All right, just like before, these are the ions that form, so let's tally up the charges. Need more minus. I don't have enough negative to balance out my positive, so I'll just get a second one of these. That looks good. That checks out. So the formula must be Ba, oops, I, 2. My brain skipped over the I for some reason. On my screen, I can kind of, there we go. Some of those pluses look like minuses because it was too thin, so now I can see it clearly. All right, there's my charges. I need more negative, so we'll just add another one in there. So this becomes 4. Now too much negative, so I gotta go add more positives over here. So now this becomes 6. And then finally, oh, I have too much positive. I'll add some more negative over here. Oh, sweet, those balance out. So let's make our formula. Al2 S3. There you go. We got sodium and nitrogen. You'll notice that we're just kind of repeating some of these. There you go. Now you do the transition metals. These are interesting. So titanium, in this instance, is positive 4. For oxygen, it's negative 2. So when I look at the charges, oh, I have too many positives, so I need more negatives, so I'll add another one. Now they're balanced, hooray! So I would have TiO2. Fun fact, this is white paint. Titanium oxide is very, very white. And then for vanadium and phosphide, sorry. I don't know how to write the letter P, apparently. There we go. So I need more negative, so we'll do this. Now I have too much negative, so I'm going to add some positive, but positives come in chunks of 5, so you're going to notice that we're going to be doing this back and forth thing pretty often. Oh, I still don't have enough, so I'll add another one. Now I have too much, so I gotta do this. Oh, when does it end? Oh, I just need one more. And so this would be V3P5. Now, there is a sort of trick that you can do where you can say, oh, okay, well, I have 5 and 3. The common factor between those would be 5 times 3 equals 15. And that'll be the charge that you should end up with. But that doesn't always work. Now, if you have two numbers that are not divisible by one another, like 5 and 3, you can't divide them into each other. There's no number that they share in common. Then this works. But up here, you can see that with 4 and 2, you might say, oh, okay, well, just times these two together, and everything should be 8. But I end up getting 4 down here as my result. And that's because these each can be divided by 2. So if there's a common number that they have that they share and you can divide it out, you can't just multiply the numbers together to figure out what the total charge will be. But if you're wondering, man, do I really have to add all of these things together? Like, do I really need 5 of these? Is this the best way to do it? You can use this as a sort of check to say, oh, okay, I need 3 of these and 5 of these, so I might as well times the numbers together to see what charge I will have at the end. All right, that is how we make ions into ionic compounds. Any questions, let me know. Now what we're going to do is, now that we know how to turn ions into a formula, we're going to go the other direction. We're going to take a formula and we're going to split it into ions. So let's do that. The first rule that you want to remember is that if you are ever working with elements from groups 1 through 8A, so if you're using the p-table periodic table, this would be groups 1, 2, or 13 through 18. Remember that you want the ones digit. Knowing which column that atom is in will tell you how many valence electrons it has and how many electrons it needs to get or lose to make an ion. For example, here's this, whatever the hell this is, cesium arsenide? Sure. We haven't worked with these elements, but they're in columns 1A. So this is 1A. And this is 5A. Okay. Elements in column 1A have, not calcium, what am I doing? 1 valence electron, so I would need to get rid of it to get a charge of +1. Whereas elements in 5A have 5 valence electrons. Apparently they have a valence comma or something. That was a really funky looking electron. Let me try that again. There we go. And they would need an additional 3 to reach their octet. So if I ask you what are the ions that combine to make these two, or to make this ionic compound, you would say cesium plus and arsenic 3 minus. And if you wanted to, you could write all the 3 cesiums out. That's fine. But if I just asked you what ions were present, you would just get away with just writing cesium plus and arsenic minus. Or I'm sorry, arsenic 3 minus. All right. Now, that's easy enough to do if you have elements from groups 1 through 8A. But what if I give you a transition metal? What do you have to do? When you have a transition metal, you have to do some calculations. You have to do a little bit of algebra. Now, something to note is that when you get a transition metal, it's always going to be paired with a non-metal. And all of the non-metals are in groups 5 through 8A. So that means that the transition metal will be a variable, like X. It'll have a charge of X. And the other ones will be knowns. They'll be constant. So oxygen, for example, would have a charge of -2. If I had this compound, for example, and I wanted to know the charge on iron, what I would do is I would say, okay, let's split this into its ions. I know that iron is positively charged, but I don't know what its charge is in this case. I know that oxygen is always negatively charged, and it always forms a -2 ion because it has 6 valence electrons, and I need to put in 2 more to get the octet. So then I get this. I have -2 times 3 is my total negative charge. I have positive X times 2 for my total positive charge. What number has to go in the blank here? And so you should be saying, oh, okay, I understand how to do basic algebra. That number has to be +3, right? Because remember, we want the whole total charge to equal 0. And that can only happen if both this term and this term equal the same thing. So what this means is that we already knew that oxygen was this ion in the ionic compound. But this iron must be +3. Now let's do another example with a different combination of iron and see how we get a different result. So I'm going to hit erase and not select the highlighter. Let's select the pen. And we'll do this one. What's the charge on it now? Well, I've got iron with its unknown charge, and oxygen is always -2. I got 2 minus times 2. So what number should go here? Well, if I'm going to balance out this charge, and I have a total -4, this has to be +4. So if I were to split these into ions, this is what I would get. Oops, hold on. I wrote 4+, but I meant to write Fe4+. There you go. So you can figure out the charge of a transition metal from the other ions, and you will always be able to do that for all the compounds that I give you. So I'm going to give you this example to try. I have tin and oxygen. Now, tin is not a transition metal. It's actually in column 4A. However, an interesting feature about tin is that it sort of behaves like a transition metal. It can have a variable charge. It doesn't necessarily have to have the charge for the column it lands in. But you might notice that in this case, it actually does. So, what are the ions that make up tin? Do the analysis that we just did. Type your answers in the chat, and we'll go over the answers together in a second. All right, you're going to notice that this example is just like what we just did with the iron. And it turns out that this is really common. If you pair two oxygens with anything... Oops, I didn't write the second oxygen here. Then whatever you have left over is always going to have a charge of 4. It does not matter what the identity of the atom is, or the ion, because the charges dictate the result. So whenever there are two oxygen atoms present in an ionic compound, I cannot find my cursor. There it is. Then you will always get a +4 charge. If you had 3 present, then you'd have a +6 charge. And so on and so forth. Now, if you have multiple of your transition metal, you're going to have to divide that total positive charge among your number of atoms. And so that's what we did with the iron Fe2O3 example. So I've given you a bunch of different compounds here. The first two do not have transition metals, so they would follow the columns 1 through 8A rule. That's easy enough. You can just look them up in the columns, and you'll eventually just start to learn, oh, okay, everything in column 1 is +1. Everything in column 2 is +2. Until you get to that point where you can identify what ion forms just by looking at what column it's in, just do the octet rule. Draw out all the valence electrons, and then try and get to the octet rule, and then make the charge that way. Once you're able to do that, and you've got the ions figured out, figure out the other ion in the pair if it's a transition metal. So for these 4 right here, you're going to have to figure out the charge on the transition metal. And it can be anywhere from 1 to 8. That's my hint that I'll tell you, is it's going to be some number between 1 and 8. Okay? Go ahead and do these. We'll go over the answers together in just a bit, and then we'll be due for a break, it looks like. So see you in a bit. one more minute to go over, and we'll go over the answers. Let me just set this up here real quick. And okay. Let's go over the answers together. We'll take our break after this. So we've got, for our first one, we've got, let me actually move the canvas up here. We've got aluminum and bromine. Aluminum is in group 3, and bromine is in group 7. Both of these are A. So I'd go doot, doot, doot. And for bromine, I would just do that. And those would be the ions that are present. So we don't even have to do any math because both of those are in the known groups 1 through 8A. Same thing for this next one. So we got calcium. We got chloride. Again, you should be able to count the number of valence electrons these have. Calcium, I'm going to do that to get to its octet. Chloride, I'm going to give it 1. And there you go. Those are the ions that make up this compound. Now let's do the transition metal ones, which have to have a bit of solving. So I have osmium, and I know that its charge is blank. We'll call it X. And I've got 4 oxygens here. And we know that each oxygen is going to be -2 because we've done oxygen all day, right? That should have been a plus there. There we go. I don't want to write it like that. I want to write 2 minus times 4. All right, so -2 times 4 has to be the same amount of negative charge as whatever X is. So what must this be? It's got to be 8 plus. So those are the ions that we get there. Osmium 8 plus and oxygen 2 minus. Totally possible to have 8 plus. Now you might think, well, wait a second, how would I get 8 plus for an element? Wouldn't that be way easier to just add however many electrons to get an octet? Remember, transition metals don't follow these same rules. They don't follow the octet rule. So there are actually extra electrons that are available somewhere that osmium is ditching in order to get to a stable configuration. And we'll talk more about that in 161 when we talk about sp and d electrons. What we're doing here is we're pitching all of its d electrons. And there's just so many of them that we can get up to an 8 plus charge. Rhenium is the same way. I really have to draw 7 of these, don't I? Look what I did to myself. What charge does chlorine have as an ion? Well, it's always -1. So X plus, Cl minus, oops. So Cl minus would be 1 minus, and there are 7 of those. So what must the X be? Well, it's got to be 7 plus. So there are my ions. Same deal. All right, down here we get more cations. I can't write the thing. There we go. And then I have 1 oxygen, and I know that as an ion, it's 2 minus. So this is all I have, but now I have X plus times 2. So what number has to go in the blank for X? Well, the only number that works is 1 plus. So for gold, each of these must be plus 1, and then oxygen must be minus 2. And then finally, same idea for scandium. So there are 3 of these. And then I have nitrogen. Remember that nitrogen has 5 valence electrons. So in order to get the octet, we would have to add 1, 2, 3 more to make it that charge. Cations are only transition metals. Or, I'm sorry, transition metals are only cations. Cations could be transition metals, or they can be elements in groups 1 or 2 or 3A. What number do we solve for when we get X here? Well, I have a total of 6 minus charge here. This has to total to 6 plus, and the number that solves that would be if this was a 2 plus. And so those are the ions that we get for this ionic compound. Scandium 2 plus and nitrogen 3 minus. All right, that is pretty much it for how we make ionic compounds, I believe. So in the next section, when we come back, we're going to do one last little bit about ionic compounds with those polyatomic ions. Hey, remember those polyatomic ions that I told you to memorize way earlier in the quarter? Yeah, we're getting to that part. So you'll see those when we come back. So I'm going to start the break timer. We'll take a 10-minute break and listen to some more Donkey Kong Country 2. So I'll see you in a bit. Oh, we had to stop right in the middle of the best song on the track, but that's okay. We'll just wind this down here. Alright, welcome back to Chem 140. We're going to finish off Unit 9, because we're almost done with it. I should probably click on this, huh? The last little bit we have to talk about for forming ionic compounds is, what are these polyatomic things that we've been talking about? Polyatomic ions are clusters of atoms that group together in a sort of molecule, but the molecule itself has a charge, and so it's an ionic compound. On the giant chart of polyatomic ions, and I forget where your chart of polyatomic ions is. Let me find it really quickly. So it's at the start of, I want to say Unit 6. Yeah, Unit 6. So if I capture this window here, hopefully you remember this right here. I don't know why it's telling me this message. There we go. Well, now you can't see it, but... So hopefully you remember this giant chart of polyatomic ions and then how there was a second page of them. So these are in Unit 6. You're going to want to know these, or at least have them handy to reference, because we're going to be using them. Every polyatomic ion has a formula and a charge associated with it. You're going to treat that like any other ion and use it in the same fashion. So you can use those to build ionic compounds. So for instance, if I wanted to make an ionic compound out of calcium and then phosphate here, I would say, okay, well, calcium has a +2 charge, phosphate has a -3, and then I do the same process. Oh, I have too many negatives, so I need to add more positive to it. So I do that. This becomes a 4. Now I have too few negatives, so I'm going to add another phosphate. So this becomes 6. We'll do this. So this becomes 6. And there we go. That would be our balance for charge. So I would write the formula as 3 calcium Ca3. And then I have 2 phosphates, so I got to put them in parentheses. That would be the formula of my ionic compound. Excuse me. In other words, you're doing this exactly the same way as all of your other ions. You just have to look up what the polyatomic ion is for its charge. Now, I might be tricky. I might, instead of writing the word, or instead of writing this, I could instead have written phosphate. And then you'd have to go look it up. So having these handy on either that piece of, or that slide, or having them memorized will help you out a lot for the questions that are coming up. It didn't erase. There we go. And again, if you ever use a polyatomic ion and there is more than one of it, you have to include these parentheses. Because otherwise you get this, which is like, whoa, that's a lot of oxygen, right? And you don't want to accidentally mistake one compound for another in that manner. All right, so I have more exercises for you. What I want you to do is take these first 4 and make ionic compounds out of them. And then on the second one, I want you to split them up and tell me what the ions are. Now, because the polyatomic ions in each of these things are the known quantity, you can look up their charge, and you can use that to solve for the transition metal. For the other two, for the strontium and the potassium on those bottom set, those are in groups 1 and 2A, so you should know their charge already. Okay? So go ahead and make the ionic compounds for the top set, split into the ions for the bottom set. We'll go over the answers shortly after. Another minute or so, and we'll go over the answers. All right, let's look at these. Let me clear the this thing. I don't know what to call it. Oh, I gotta get rid of this. There we go. Not sure why it does that. I have a workaround, that's fine. All right, so I'm in the wrong color. I mean, same deal that we've been doing all period, right? Need more negative. There we go. That checks out. So my formula will be barium cyanide. Sorry, I had to squirt bottle the cat there because she won't stop bugging me. She wants to be hugged. She just wants me to hug her all the time, but I have to teach. So, sorry, Maya. Got sodium and chromate. That should be an R. There we go. Same strategy. Need more positives here, so we'll just do that. That makes this 2. We're all good. There's the formula for sodium chromate. Then we have ammonium. It's hard to see that there's a plus on there. Let me make this bigger. There we go. There's ammonium, and then we have sulfate. Need more of this so that I end up with 2 positives. That balances out. So the formula would be NH4. I need 2 of those, so I got to put it in parentheses. SO4. And finally, aluminum and hydroxide. I need more hydroxide so I can get this to balance out. There's my formula. All right. Now I got to go backwards. We got to break these into our ions here. I'm going to run out of space, so let me just clear this text field here. Or just clear my canvas or whatever. So we got strontium and then carbonate. So I know that from the periodic table, strontium has 2 valence electrons. And if I get rid of them, that makes my ionic compound. And I also know that by looking at the polyatomics list, those are the charges on carbonate. So that's easy enough. I'm going to skip ahead to potassium sulfide, or sulfite, and do the same thing. Because I know each potassium is +1, and I know that sulfite is -2. Because I can look up sulfite. That's easy enough. And also potassium is in column 1. But these other ones down here, I'm going to have to do the solving trick for. So we got iron 3. Oops, I already said what it is, but... So there's my iron, and I don't know what its charge is. But I've got 3 cyanides, and each of them is 1-. So if this is the scenario we're in, the only number that fits here must be 3+, so that must be iron. It's charge, and then cyanide would be Cn-. And then finally, this crazy mess that we have here. That's not where the 5 goes. What am I doing? So I got 5 phosphates. Let's write them all out. Keep in mind, phosphate is P and O, so phosphorus and oxygen, and is not polonium. Be very careful you don't accidentally do something like this, because that would look like polonium, which is a radioactive metal. You don't want that. So make sure you capitalize that O, make it nice and big. And then I have vanadiums. I don't know what the charge is on the vanadium, because that's my transition metal. We're going to have to solve for that. But I do know what the charge is on phosphate, because I can look that up. They're all -3. All right, so I've got -3 times 5. That has to equal whatever this number is times 3. So the number that fills in that gap here is 5+. You'll notice that I've used vanadium twice, and it often at times ends up being 5+. It's not always 5+. In fact, vanadium can be anywhere between 2 and 5. But 5 is a common one for vanadium. And then, of course, we have phosphate still, like that. So those are the ions that make up vanadium 5-phosphate. All right, that's how we use polyatomic ions to determine charges and resulting ionic compounds. So make sure you get in enough practice with making these ionic compounds, because this will be a very key skill going into 161, where we're going to use it more. Okay, the last thing that we're going to do today is sort of our segue to getting to Unit 10 here. Unit 10 is real short, so we're going to finish it very quickly tomorrow. I'll talk about why tomorrow in just a second. But this last section helps us figure out the difference between which compounds are ionic and which ones are covalent. And there's a very simple rule, and you probably already know it. An ionic compound has metals in it, and a covalent compound only has nonmetals in it. Now, there are other differences too. So we've already established this one right here. Metals and nonmetals combined together to make our ionic compounds. In covalent compounds, we're only going to have nonmetals. Now, we've also mentioned the formula unit. Remember how in a lattice, formula units are just the simplest repeating pattern? But in reality, you don't have a molecule of an ionic compound. You have a repeating array of ions that spread out infinitely in all directions, basically. And then finally, we showed the electron transfer at the very end of the previous lecture last week. We move electrons around so that everything gets an octet. Now, in Unit 10, what we're going to find out is that covalent compounds do completely different things, which is why they have a different type of bonding. For example, covalent compounds form independent molecules. Water is a covalent compound. A water molecule is not attached to another water molecule in any way. Each H2O is distinct and independent, and you could separate them very easily if you had tweezers small enough. With an ionic compound, you couldn't. They'd be like a bunch of little magnets stuck together. Covalent compounds don't transfer electrons. Instead, they do something called electron sharing, where we start double counting the electrons. As long as an atom thinks it has 8 electrons to satisfy the octet rule, it will be more stable. But there aren't enough electrons to do that in covalent compounds, and we'll show that in tomorrow's lecture. And then finally, like we just said, nonmetals only. Now you'll notice this down here. There is one exception to the metals and nonmetals rule, and that is actually this one. Ammonia is a polyatomic ion. And if you form a compound with ammonium, you will get an ionic compound. So if you see ammonium, be very careful. Okay? Even though there are no metals inside this compound, there is an ion on it overall. And so anything that contains this will be ionic and not covalent. Okay? That's important when you get a question that just says, categorize ionic versus covalent. If you see NH4 in there, remember, that's NH4 plus as an ion, and it will be an ionic compound. And down below, I have a bunch of examples of ways that you could include ammonium. So I have a slide here. I think this is the last slide. And what I want you to do is tell me ionic or covalent. So just go down the list, write all the ionic ones in the chat, and then hit a space or some other punctuation, and then write all the covalent ones. We'll go over the answers together in a second, and then I think that might be it for today. Yeah, that's all we're going to do. So see you in a bit. All right, one more minute to finish up. We'll go over the answers. All right, so what I'm going to do to identify these is I'm going to just grab the highlighter here. So we'll say that anything that's highlighted in blue, this will be ionic. And remember that when we're looking for ionic compounds, we're looking for metals. So silver's a metal, so this must be ionic. Sulfur, not a metal. We're going to skip it. Hydrogen, not a metal. Nitrogen, not a metal. Be careful, NH3 is not ammonium. That's ammonia. In fact, let's write those down here. So this is ammonia. Notice the difference here. I'm muted, aren't I? Wait, no, I'm not muted. Huh? Can you guys hear me? Hello? Hold on. That's weird because it says, you can hear me, okay. Sorry, I've been having issues with my headset, like it was very crackly, so someone saying, oh, you're muted, I can't hear you, even though I can see, like, it's receiving something, makes me think, oh shit, something is wrong with my headset, and I'm gonna have to replace it. I hope not. I hope I can make it through the quarter before I have to do that. Okay, cool. So, just note the difference between ammonia and ammonium. That's easy to do. Just, yeah. Sorry about that. That's easy to do. So be mindful of that. So NH3 does not have any metals in it, so we're not going to mark it as ionic. But NH4 is ammonium, and so we will mark it as ionic. Down here, potassium is a metal, we'll count it. Iron's a metal, we'll count it. Platinum's a metal, we'll count it. So those are all our ionic compounds. So everything else, we'll pick purple, because when do I ever use this color, right? Everything else must be covalent. And so the ones that only have nonmetals in them, that are not ammonium, are covalent. All right, well, that's all we have for this chapter. In fact, hold on, let me put the sound up here so that we can do our little hooray. All right, that's Unit 9. let's talk a little bit about what's going to happen for the schedule this week, because there's sort of an oddity in the calendar. And I only really noticed this. I don't know why I did this, so I'm going to put this on the screen here really quickly. All right, so here's our calendar. We're right here. This is today. You'll notice that this is not what we did today. Instead, we did this because, remember, we lost this. Wait, did we? We didn't lose a day in this class. I'm just behind. That's all. Okay. Oh, I did lose a day. Yeah, I lost Tuesday because I had to go to the damn hospital. That's right. Okay, so we lost a lecture day on Tuesday, and so everything got pushed back a week. Or not pushed back a week. We got pushed back a day. So we're actually done with this section here. But we were supposed to do Unit 10 and then start Unit 11 tomorrow. You'll notice here that it just says extra lecture if needed. And Q&A otherwise. Like, wait a second. There isn't an issue here. I don't know why I think there's an issue here. I thought everything got pushed back a week or something, but yeah, I don't know why. Maybe it's just this down here that I'm confused about. Anyway, it says here extra lecture if needed. What we're going to do tomorrow is I'm going to lecture on Unit 10 because Unit 10 is very short. It's like, do I have it up here? Yeah, here's Unit 10. So you'll notice that there's only one section in it. It's like 20 slides long. So we're going to do that tomorrow, and then we'll do our Q&A. So tomorrow we'll actually have a lecture component to it. And then after, we'll do the question and answer session if anybody has any questions. So I expect that what will happen is that the first hour will be the lecture. And then after that, we'll have the Q&A. And then on Thursday, we'll do Unit 11. We won't finish Unit 11. That's fine. But we'll get pretty far through it. And then we'll finish up Unit 11 in week 8. And then we'll be more or less back on track. And if we have to, then I will just continue the extra. Oops, you can't see that. We'll just continue here until we get through chemical equations. So I don't expect that we will be that far behind. Okay. There is a lecture during week 10 on solutions, and that is because the lab worksheet number 5 does count for solutions. So a lot of these Wednesday classes coming up are going to actually be lectures. So just be mindful of that. And I'll bring up the schedule on occasion to remind us just what's going on. Okay. Other than that, though, that's all that I really have planned for today. So after tomorrow's lecture, we will have a quiz on Units 9 and 10, and that will go up. You'll have a week to do that. Unit 11 also has its own quiz, and Unit 12 also has its own quiz. And the units they're not super long, but they're going to probably only take 1 or 2 lectures, and so another quiz is going to show up, and then another quiz is going to show up. And you're going to notice, like, wow, that's a lot of quizzes. Holy shit. So stay on top of the quizzes, because there's going to be a bunch of them coming up as the quarter progresses and as we get towards the end, because we're almost done. This is week 7, so there's... How many lectures am I counting? 1, 3, 5... There's like 6 or 7 more lectures left, and then we're finished with the class. You'll take a final. So blink and you'll miss it, and we'll hopefully be the spring quarter sooner rather than later. So, all right, have a wonderful rest of your day. I will see you tomorrow for that Unit 10 lecture. See you then.